So we learned from Newton's second law that when a net force is applied to a body, it causes the body to accelerate. But now we're in the spinning realm. We were talking about rotating things, and we want to know what causes a body to have angular acceleration instead of just regular acceleration, or what we might refer to as linear acceleration, even though it's curvy sometimes. If we have an object like a door attached to an axis of rotation and allowed to rotate because of the hinges, what makes the door open or close? Well, the answer is, of course, a force is applied, but doesn't it matter where and how that force is applied? So if we have this door here, and if you push this door very close to the hinges, it's pretty hard to open and close it. If I were to apply a force here, it'd be very hard to do anything. In fact, if I were pushing right on the hinges, it does nothing to open or close the door, right? But if I push far away from the axis of rotation, near the door handle, like this big force arrow here, it rotates really easily. So if you're pushing a door all the way at the end, that's the easiest way to open or close the door. So evidently it matters how far away from the axis of rotation you're applying the force. The farther away, the more effective. How about if you apply a radial force on the door, which would be inwards or outwards, so like this kind of a force. If you just push on the end of a door, does it open or close? No, it doesn't do anything at all. So we have two things that determine the magnitude, evidently, of rotational acceleration. Aside from just the magnitude of the force itself, right? If you push harder or less hard, obviously that's going to affect it. So we have how far away the force is from the axis of rotation. That's the first thing we identified. Can't push at the hinges, better to push on the ends. And we'll call that vector r. And how orthogonal f is to r. So if our r vector is this one here, let me erase some of these other guys. If our r vector is here, this is how far away our force is being applied. And our force is this one. Then what we care also about is how orthogonal f is to r, because we said that if f is directly parallel, it's not going to do anything. But if it's perfectly perpendicular or orthogonal, then it's going to have the maximum effect. So the larger the magnitude of f and r, the larger the acceleration, for one. So we want them to be multiplied. Okay? So we're going to kind of work our way up to arriving at a little equation here, or a definition here. But one thing that we know is that the angular acceleration, alpha, must be proportional to this r vector, right? The farther away you push, the better. And the stronger the force, the better. So they will both be in the numerator, multiplied. But also, again, we said that the more orthogonal f is to r, the larger the acceleration will be. We have a vector multiplication type that will tell us that. Do you remember which one it is? Which vector multiplication tells you how perpendicular two vectors are? There's one that kind of tells you how parallel they are, how in line with each other they are, and the other one tells you how perpendicular they are to each other. Is it the dot product or the cross product? It's the cross product. And so we can say that the angular acceleration is proportional to r cross f. And the cross product, remember, is just r f, the magnitude of each, multiplied, times the sine of the angle between them. The angle between them. So it would just be, I can't rotate it the way that I need to show you, but the angle between them here. Maybe you can see that. And the reason that the cross product does this for us is because this sine, if the angle between them is 90, then sine of 90 is 1. And so you have the full r times f. You have this multiplication maximized. But if they're anything less than 90 degrees angle between them, then sine reduces from 1 to less than 1. And so you get some lessened total multiplication. And then if they're completely parallel, sine of 0 is 0. So if they're completely parallel, then the whole multiplication just turns to 0. So that's how the cross product tells you how perpendicular they are. So this quantity we've discovered here, this one here, written concisely, we give this a name, and we call it torque. And that's denoted with a tau symbol like this. And it is a vector because cross product is also known as a vector product, and the result is a vector. So torque is the r vector cross the f vector. And you've probably heard the word torque before and known that it has to do with wrenching on things or motors. It's relevant, right? So it's spinning things. And so this is just the distance from the rotation axis, and this is the magnitude, this is the force that's pushing at that distance. And just like any cross product, the direction of the torque vector is determined with the right-hand rule. And with cross products, it kind of gets a little bit non-intuitive, but you would just take your, so if this is, let's say this is our r vector here, because our axis of rotation, let's say, is this, so it's something is rotating around this way, and let's say our f vector, how can I show this best to you? Our f vector is like this then, right? And so we would say r cross f, right? And so it would be r cross f, because if you bring this guy tip to tail, r cross f, and your thumb sticking out tells you in the direction of the torque vector. It's hard to do right hands with these controllers, so you can't see my thumb, but hopefully that makes some sense. So that's torque, and we're going to pick up with that in the next video.